Okay, in this video I want to introduce the static keyword again. I introduced local static variables in the pointers and references lesson, but here we are going to talk about the static keyword when applied to global variables and functions, and then also member variables and functions. But to really discuss the static keyword, I also have to talk about scope again in a bit more detail, and actually the discussion on static member variables and functions will carry over to the next lecture, where we'll talk about the this pointer. To get started, the static keyword can be applied to global variables and functions, local variables as we talked about before, and I'll do a quick recap of that later on, but then it can also be applied to struct and class, member variables and functions. Now depending on the context, static means something different. So I'm gonna try and explain it to you step by step, and then through the examples and then also some of these summaries, hopefully it'll help you avoid some of the confusion around the static keyword. Okay, so just a quick note here. When I'm talking about identifier scope, I'm referring to the sections of code within which the identifier is available and can be used. So if you have some integer x, for example, at the top of your file, some global variable, for example, that identifier x is accessible to the rest of that file, including main and all of your other functions, so everything following that identifier. We'll actually talk about the global scope in a bit more detail in this video as well. An identifier is in the global scope if it is not declared static or declared in a compound statement. So the scope of this is from the declaration to the end of the source code file. Again, that is where the identifier is available and can be used, but it's a bit more complicated than that because the scope of a globally declared identifier can be extended to other code files by using the extern keyword, as I'll show you here in a second in Visual Studio. Now only classes and namespaces should be declared in the global scope. If you have too many identifiers in the global scope, you do what is known as global namespace pollution, and you can have identifier conflicts. Next, before I show you an example of this in Visual Studio, you also have something called file scope, and it may seem similar as the global scope, but is not. The keyword static is going to give global identifiers file scope. And so what is the scope here? The scope is from the declaration to the end of the source code file. Now file scope identifiers cannot be extended to other code files by using the extern keyword. The identifiers are basically hidden from other source files, similar to when you use private members in a class, for example, or in a struct. File scope identifiers do not expand or pollute the global namespace, as it is called. And again, you want to avoid global namespace pollution because global namespace pollution can lead to identifier conflicts. So instead of using global identifiers, you should instead use the keyword static to give those global identifiers file scope. So in this example, I want to show you what the keyword static is going to do when applied to a global variable or function. And to do that, I have to go and create another source file here. So I'll right click on the project, add new item. I'll select C++ file, so .cpp. By default the name is source.cpp, and that's fine. And I'll just click add. Okay, so we have our main source file now, .cpp file, and we have a source.cpp file. In the source.cpp file I'll create some integer variable, and I'll define that as well. I'll set that to 5 by default. I'll go back to main now, and I'll create a variable called var again. It's an integer and I set that to 6. You can see that I do basically the same thing in both source files. I just changed the definition to something else. I'll just build and run this and we'll actually get an error here. We'll get some error here, int var already defined. So that's what I talked about previously. Both of these variables are now in the global scope. In these examples we have very small programs, but you can imagine having a huge program with hundreds of thousands of lines of code and maybe hundreds of source files with multiple programmers working on that program. And if those programmers use global variables too often, then that will again pollute the global namespace, and that can lead to conflicts as we have here. So we have a conflict because we have this var variable, even though it's in a completely different file. And you can see I'm not including that file. It's not a header or something that I'm including. I'm only including iostream. So I'm not including that file, but we are still getting a conflict because var is in the global namespace. To sort of hide that here in the source.cpp file, we can do this. We can do static int var and set that to 5. And that basically hides this var variable now in this particular file. In main, all I'm going to do is I'm going to print out that var, and in this case you'll see the program builds and runs, and we get 6 printed out. We don't get any errors or warnings. So basically the var from that other file is ignored now, and we essentially use the local one. Now stepping back for a second, let's say I have this here. I remove static. How do I access this var here now from a different file? Well, I'll go and remove this. Okay, I'll use the extern keyword, specify the type, and then we have the variable name, which is var. Extern specifies that the variable or function is defined in another source file. Extern should be applied in all files except the one where the variable is actually defined. So in other words, in all source files where you don't have the definition, you will apply the extern keyword and essentially do a declaration, and that will then refer to the actual definition of that global variable. You want to make sure not to try and redefine that global variable because it's already defined, and that can give you an error if you try to redefine it. Again, remember now that this var here in the source.cpp file is now in the global namespace or in the global scope, or in other words, it is available globally. If I build and run this now, it should print out 5 and no errors or warnings. This now refers to this variable that is declared in the source.cpp source file. Now I don't recommend that to do this because again we are now polluting the global namespace or the global scope basically with this variable. And what happens is, again, let's say later on some other programmer creates a source file and uses another variable called var or whatever you have. You can have a conflict. So instead, I'm just going to delete that. I'm going to go back to the source.cpp file and I'll make sure to use the static keyword. Another tip for you, and something that I've seen quite a few times, is to prefix the identifier with an S. You can do S and then var. So you can do it like this, but it's more common to have S underscore and then start your identifier name. This just makes it clear that it is a static identifier, so a static variable. And in this way, this variable now is in file scope. So it's available to use in the file from where it's declared to the end of the file. And the same thing with functions. So okay, so I have this demo function now, just some function that prints something out. And that is basically now in the global scope too. So if I go to main and again, let's say I'm just some programmer going about my business and I'm declaring and defining this function here and I want to use it in the main function. Build and run and we get an error all of a sudden. Why is that? Well, that function is already defined. And if I go and look in some other source file, it is defined already. However, if I now have a static function in this other source file and I go back to main, build and run, then this will work fine. We get by instead of hello. Of course, if string is silly, you could maybe say hello from source.cpp and then also hello from main.cpp. With the keyword static applied to this function now in the source.cpp file, I'll go back to main.cpp. If we build and run this now, we should get hello from main printed out. So hello from main.cpp. If I go back to the source.cpp file and remove that, a static keyword, go back to main. I'll do extern, void, and demo function. Build and run, and that should print out hello from source.cpp now. Okay, so just a quick demo on how the function works. Now we don't need the source file for the rest of the demo, so I'll just close that off, clicking this close button. And you can save that if you want. Now to open it up, you can always just go in the Solution Explorer, double click on it to open it up again. So what you want to do with these global identifiers is you want to use the static keyword to make sure that those are in file scope, and in that way they don't pollute the global namespace. Let's take a step back and talk about the memory segments used by a program again. I talked about this in the pointers and references lesson, where we mainly discussed the difference between the stack and the heap memory. Well, you might be thinking the static is sort of confusing. Why does it make those identifiers act sort of differently than what we are familiar with regular variables? Well, if you think about it for a second, the heap that we discussed in the pointers and references lecture, we don't just allocate variables on the heap automatically. We have to sort of create a new dynamic variable and return that address and store it in a pointer, and then we can use it. So it's a different way of working with that memory and working with those variables. And so here, if you look at static again, this memory segment stores global and static variables. Okay, and that's going to include your local static variables and static data members. Then next we have the stack again, and basically memory for your objects and variables will get allocated and deallocated automatically depending on the scope. So when you go out of scope, out of a compound statement or a function, then that will clean that up automatically. Again, that's not the case with dynamically allocated variables. And static is again another memory segment. And the global or static variables that you go and store in that memory segment will typically be created before main actually executes, the main function. And then it's typically destroyed when the program terminates. So not when you use delete or when a function terminates or something like that, but instead when the program exits. From the memory segments, and thinking back to the heap memory versus the stack memory, maybe this will lessen the confusion as to why static identifiers work a bit differently than what we are used to with regular variables, so local variables, in functions and so on. And that again has a lot to do with the fact that they are in a different memory segment. A recap on local static variables. So in functions, for example, initialization only occurs once. The first time the function executes, you go and initialize that variable. The value of the variable will carry over to each successive function call. In other words, it's only initialized once, so it's not going to redeclare and redefine, or in other words, reinitialize that variable each time you call the function like it would with a normal stack variable. It's basically going to skip over the initialization part and only do the rest of the statements in the body. In this case, I have a silly example. Each time you call this function hit, it's going to increment the hit variable, and then it's going to print out how many times you've hit yourself, basically. The memory that is allocated for the variable is going to persist for the duration or the lifetime of the program, and then the memory is going to be reallocated when the program ends, as opposed to when the function terminates, as with regular variables, so regular stack variables. A quick note on class scope. An identifier has class scope if it is declared inside a class definition, and the scope is anywhere in the class definition and in the bodies of member functions as well. Next, I want to talk about static members. Class members, so member variables and member functions, can be declared as static. Here I just have some entity class. In the body, in the public section, I have a static function, getMember. It's going to return an integer, and in the body of that function it returns s_member. I prefix that with an s and an underscore to make it easy to see that that is a static member. And that static member is in the private section, so you can see we have static int s_member, just as an example. So at this point the static member variable is declared, but is not defined yet, so it will be considered an incomplete type. And if you don't go and define that, you'll get an error, as we'll see later. So following the body of the class, I go and define that static member in the file scope. I have to fully qualify the name, and so basically I do integer entity, which is the class name. I use the scope resolution operator followed by the member, in this case s_member, and then I can assign it some value. So if you try and define it in the body of the class alongside the declaration, then you'll actually get an error, as we'll see in an upcoming example. There's a way for us to define it inside the body of the function, but I'll show you that in an example later on. A static member variable is data associated with a class rather than with an instance of the class, so an object in other words. Each object maintains its non-static member variables, but a single copy of a static data member is retained across all instances of the class. So in other words, you only have one instance of that variable. It doesn't matter how many times you instantiate that class, you only have a single copy of that static data member. So you can almost think of it as an organizational thing. The static member is associated with the class instead of being like a global variable. Now what's useful about static members? Well, one example would be, let's say you want to keep track of how many instances you have of a particular class. You want to keep track of how many instances there are of some enemy class. Then each time you spawn or create an enemy in your game, you can increment the static member that keeps track of the number of instances. And each time you destroy an enemy, you can decrement that static member. Static member doesn't affect the size of an instance of the class, since the static member variable doesn't really form part of the instances of the class. Again, they are declared in class scope, but they are basically defined or initialized at file scope. The static member function is also associated with a class, rather than with a particular instance of the class. We can invoke a static member function using the class name, followed by the scope resolution operator, and then the static function name. So in other words, we can use the static member function without having an instance of the class. In this first example, we have a struct entity. It has this member, an integer, and I simply have a function void toString, and it's going to print that member out. So I'm just using a struct here because all the members are public anyway, and that makes it easy to demonstrate, so I don't have to do a bunch of getters and setters and so on. Okay, in main I instantiate entity. I create an entity called entity1, and I use list initialization to initialize that member to 5 here, and then I do entity1.toString. We'll run this and that should print out 5. Okay, next let's say we want to create a static member. So this member is now static. You can already see some squealies right here. If I build and run, we'll get an error. And the reason is that this here is not really part of the object itself. You have to define that in a different way. So I'm actually going to remove that initialization section, and I'm going to initialize it in a different way. And before I do that, actually static, so this name here, I'm going to change to S_M, just to make it easy for us to see, okay, that is a static member. Of course, we now have to update this right here as well. Give that some different value, maybe 700 or something like that. So this right here is the declaration. And this right here is the definition in file scope basically. If you try and do this again, you'll get an error, so a redefinition error basically. So you want to define it once, and then in main I still have that entity, so I do entity1.toString, build and run, and this should work fine. Prints out 700 as we expect. Okay, moving on here, remember that this is just the definition, or basically an initialization, and without this here we have an incomplete type. So if you only have the declaration, then it's an incomplete type. You cannot go and do something like this. Okay, you'll get an error. You can try and build and run that, and you'll get an error. Now it talks about inline here, and so on. We'll talk about this inline a bit later on in the video. You can actually initialize it as inline, but again, we'll demonstrate that to you a bit later. So this here is considered an incomplete type, and once it is actually undefined, then it is a complete type. Remember that when you instantiate a struct or a class, or when you create an object, all of your members will be defined by default, even if they contain garbage. So for example, if you have some struct or class where you do not have user-defined constructors, then as we talked about before, the struct or class will have default constructors, and those default constructors will basically do nothing. Now in that case, even though the default constructor does nothing, your members will still get initialized to some garbage value. Well, that doesn't quite happen with the static member. It doesn't get initialized when an object gets constructed because it's not really associated with an object, it's really associated with the class. And it's also in a different memory location as I talked about previously, and for that reason you go and define that separately. Okay, so hopefully that makes sense. And with that defined now, that is referred to as a complete type. Okay, and if you try and comment that out, build and run, you'll also get an error. Unresolved externals and so on. Next, let's go and change that member variable. I'll change that to something like 44 and see if this works fine. That builds and runs and prints 44 out. Instead of 700, it prints out 44. Now I'm going to declare another entity, and I'll just call that entity2. I'll do entity1.toString and entity2.toString, and they should actually both print out 55. And as you can see, that is exactly what happens. It prints out 55 each time. And again, that is because the S member is actually associated with the entity class itself, and it's not really associated with a particular object. You can think of it as a single object in the static memory segment, and that is associated with the entity class, or in this case a struct, but we only have that one object which is associated with that entity struct. So it's defined right here, then we change it to 44 and we change it to 55 again, even though we are using different objects. You might be thinking, well, since the static member is associated with the entity struct itself and not with a particular object, why can't we just access it directly? Well, that's actually what we can do. So instead of doing this, I'm going to use the entity name directly, followed by the scope resolution operator, and then I access that static member and then set it to 44. And here I can do the same thing. So this is what we did previously, the same member we set twice, first to 44 and then to 55. And that's why for both of those entity instances, it printed out 55. So here I can actually just remove that. And the second entity as well. Build and run, and that should print out 55 again. You might be thinking, well, okay, we can access that member without having an object now. Can we do the same thing for member functions? Well, yes, we can. So what I'm going to do is scroll up to toString here. And this is now a static void toString function, and it's going to print out a static member. So now instead of doing this, we can actually get rid of all of that and the object itself. And I'm just going to remove this here as well. And now with IntelliSense, you can see we can do two things using that entity identifier. So I'll do toString, build and run, and we should get 55 printed out. This is really cool because we can use functions and members that are sort of associated with a struct or a class without even having to create any objects. You might be thinking, how is this useful? Why is this even relevant? Well, in an upcoming section, I'll show you in Unreal Engine where they have their own fmath struct, which contains a bunch of helper functions. And of course, you can think it would be a hassle to create an object each time you want to do some math. You just want to call some function, right? And they use static functions in their fmath struct, as I'll show you in an upcoming subsection. And so that's just one example. Now a few more notes here. If I have another member, let's say I want to do this now, so I have static void toString, and I want to print out this member here, member2. And if I use non-static member variables in static member functions, then I'm going to get an error. If I try and build and run this, of course, I'm going to get an error. And the reason why is, again, we are setting a member or using a member, and we are using this function without having any object. Whereas this member2 now, relies on the fact that we have a valid object. But if this function was not static, so is this a non-static member function, then this is fine. I can do console output, I can use the static members, and I can use the non-static members as well. Now of course we'll get an error right here because this function is not a static member anymore. And in that case, if I go and create an entity, I do entity1.toString, then we'll have this member. Now it's going to have garbage at the moment, so I'll just give it some silly value. It will be initialized to that value when we go and instantiate that entity. So it will print out this value here, which will be 55, and then 500 for member2. Pull and run, and that's what we get. Next we have inline static members. An inline static member variable can be defined in the class definition. This was introduced in C++17. In the private section you can see I have inline static int s_member for some static member, and I just define that to some value. I'm showing you both ways because you won't always see this. Especially in older code you might see what we've done previously, where it is declared in the body of the class but defined in file scope, so outside the body of the class. Okay, I'm back in the example where we have the entity struct and we have static int and s_member. I'll set that to be an inline static member. Just some cleanup here, and we are not going to do this definition outside now. We'll do that right here inside the body of the struct. If we want to use that function, we need to make it static as well. Then I'll just go and remove all of that stuff. And now currently if I build and run this, I'll actually get an error. I'll just build and run it so you can see what I mean. Inline variables require at least C++ 17. How do we enable that? Well, you can right click on the project, so not the solution, but the project right here, and go to properties. And under general, under C++ language standard, you have the section that you can change. You can also get to that by going to project and then properties. Then under the general section, I'll use this drop down and I'll select C++ 17. Apply and OK. You'll notice these squigglies go away. If I build and run now, this works fine. So a bunch of things I wanted to demo for you in this first example. I'll move on now and show an example in Unreal Engine of how static members can be useful, and then later on we'll do another quick demo for you. So a quick example for you on where static is useful. This example is based on a game that I built in Unreal Engine. This is a small game where I have a paddle that moves to the left and to the right. You have an apple tree, and that apple tree spawns apples, and you are trying to collect those apples. So I have a function here called spawn apple, and every second that tree is going to spawn an apple that you are going to try and collect again. And instead of spawning the apple in the center of the tree or on a specific location each time, I found that was a bit boring. So I decided to spawn either to the left or to the right. Give that about 50-50% chance. You never know which side of the tree the apple is actually going to spawn. And that is based on this frand here is going to return a random float between 0 and 1. You can see the syntax right here. I have something called fmath. And this is a struct in Unreal Engine which contains math helper functions. And the reason why Unreal has its own math helper functions is to have platform specific implementations. Okay, so this frand right here, I'll right click on it, and in this case you can pick definition, or I'll just go to the definition. As you might have guessed, this is static. Now they have this force inline macro, don't worry about that. The type is float, and this is of course the function name, so frand. And this is basically the definition right here. So you have the body. You have a bunch of other static members here, so you have rand and so on. Just close that off. Based off of that result, I offset the spawn location, and then I do the spawning of that apple in the game world. And instead of having to create an object, those helper functions are associated with some struct or with some class. Again, static allows that functionality. So I hope this bonus section was interesting to you. Okay, one more demo for you and another example of where static data members can be useful. In this example I have a class called enemy. In the public section I have the constructor and I have a destructor as well. In the constructor you see I increment this member, this static member, s_enemy count. So each time we instantiate this enemy class, that is going to increment enemy count. Then I print this out here, an enemy has entered the game, and then I print out this line as well, current enemies, and I print out s_enemy count. Now just to be concise, I did not implement a helper function. You could go and implement a helper function such as get enemy count or something like that. Then in the destructor, I do decrement s_enemy count. So I'm going to decrement that enemy count, and then I print out an enemy has been destroyed, and again I print this line out, current enemies, enemy count. Following the definition of the class, or outside the body of the class, I have the definition of enemy count, set that to 0 by default. Then in main, I instantiate enemy1, and then I do 2 more here in a compound statement. And then down here I have a pointer and I have a dynamic object on the heap. And of course I want to deallocate that object again, so I do delete enemy4. Okay, I'm gonna build and run that. Let's see what happens. So remember we had 4 enemies. Once we entered main, you construct 1 enemy. So current enemy is 1. Then we enter the compound statement and we create 2 more enemies. So an enemy has entered the game, current enemy is 2. Another enemy has entered the game, current enemy is 3. Then we exit the compound statement, and that will of course delete the local variables. So an enemy has been destroyed, current enemy is 2, and then we'll do that again, so we are now at 1. That was the first enemy we created, so enemy 1. Then we go and allocate an enemy object on the heap. So we'll get this again, an enemy has entered the game, current enemy is 2, In the next statement, we delete that object on the heap again, so we get an enemy has been destroyed, current enemy is 1, and of course once we exit the main function, the remaining local object will be destroyed, which was that initial enemy, so we'll get an enemy has been destroyed, current enemy is 0. This is handy again for keeping track of how many instances you have of a particular class or struct. So that brings me to the end of this video. It was quite a long one, but I did not want to rush it. I wanted to sort of take my time and try and explain it to you properly using various examples. I hope it was useful to you and that you understand what's going on. And this clears up the confusion on the static keyword, because you'll see it used in different contexts.